The extinction of the dinosaurs, approximately 66 million years ago, marks one of the most dramatic and pivotal events in Earth's history. This catastrophic event wiped out nearly 75% of the Earth's species, including all non-avian dinosaurs, paving the way for mammals and eventually humans to dominate the planet. This article explores the last days of the dinosaurs, examining the prevailing theories about the causes of their mass extinction. The Cretaceous-Paleogene (KPG) extinction event, which occurred around 66 million years ago, marks one of the most profound turning points in Earth's biological history. This event led to the abrupt termination of more than three-quarters of the planet's species, including all non-avian dinosaurs. The most distinctive hallmark of the KPG boundary is a thin layer of sediment worldwide, enriched with a rare element found in extraterrestrial objects, iridium. This geological signature provides compelling evidence of an extraterrestrial impact and has been pivotal in understanding the dynamics of this mass extinction. Geological and iridium analyses indicate that the asteroid impact at the Chicxulub crater in present-day Mexico was the primary catalyst for this mass extinction. The aftermath of this colossal impact had immediate and devastating global implications. The force of the collision would have released an enormous amount of energy, triggering wildfires, tsunamis, and atmospheric disturbances. The debris, ash, and gases expelled into the atmosphere would have created a barrier that blocked sunlight for an extended period, severely disrupting the Earth's climate. The environmental fallout from the impact had a cascading effect on the planet's ecosystems. The blocking of sunlight cooled the Earth's surface and interrupted photosynthetic processes, leading to a dramatic decline in plant life. This decline, in turn, had a dire impact on herbivorous dinosaurs that relied on plant life for food, which subsequently affected the carnivorous dinosaurs that preyed on them. The disruption of food chains, combined with the harsh environmental conditions, created uninhabitable ecosystems for many species. Further compounding the catastrophe were the significant geological and climatic shifts that had been occurring during the late Cretaceous period, such as volcanic activity and changing sea levels. These factors likely exacerbated the environmental stresses already placed on living organisms, leading to their inability to recover from the asteroid's impact. The KPG extinction event not only highlights the vulnerability of Earth's life forms to cosmic events, but also underscores the interconnectedness of biological and geological processes. The event redefined ecosystems globally and paved the way for the rise of mammals and the eventual dominance of humans. By studying this pivotal moment in Earth's history, scientists gain crucial insights into the resilience of life and the potential threats that could lead to future mass extinctions. The asteroid impact theory remains the most compelling explanation for the mass extinction at the end of the Cretaceous period, approximately 66 million years ago. This theory is supported by a wealth of geological evidence, including the presence of a worldwide layer of sediment enriched with high levels of iridium, an element more common in extraterrestrial objects than in the Earth's crust, and shocked quartz, which is formed under extreme pressures typical of a massive impact. The focal point of this theory is the Chicxulub crater, located on the Yucatan Peninsula in Mexico. The crater spans about 150 kilometers in diameter and was formed by an asteroid estimated to be about 10 kilometers across. The impact would have released energy equivalent to billions of atomic bombs, creating a massive shockwave and an enormous ejection of debris that spread globally. This debris included particles that blotted out the sun and cooled the planet's surface, drastically altering the climate. The environmental aftermath of the impact was catastrophic and far-reaching. The immediate vicinity would have experienced fires and a massive tsunami, devastating regional ecosystems. Globally, the debris and particulates thrown into the atmosphere likely led to a nuclear winter, with significantly reduced sunlight reaching the Earth's surface. This reduction in light and heat would have severely disrupted photosynthesis, leading to the collapse of plant-based ecosystems and the herbivores that depended on them, followed by their predators. Furthermore, the impact would have caused significant amounts of sulfur from vaporized rock to enter the atmosphere, producing sulfuric acid aerosols that contributed to acid rain. This acid rain could have had deadly effects on terrestrial and marine life, further exacerbating the environmental crises. Studies of geological formations from around the world provide evidence of these dramatic changes in the form of sedimentary deposits and fossil records that show a sudden disappearance of many species. The rapidity of these changes suggests that the recovery from this extinction event was prolonged and complex, involving significant shifts in the biodiversity and dominance of species across the globe. This asteroid impact theory not only explains the suddenness of the extinctions observed in the fossil record, but also aligns with models of atmospheric and environmental disruption that could account for the wide range of species affected. As such, it remains a critical framework for understanding one of Earth's most significant mass extinctions. In addition to the asteroid impact theory, significant volcanic activity during the Cretaceous period is another factor considered crucial in understanding the mass extinction that marked the end of the era. This volcanic activity, particularly the massive eruptions that formed the Deccan Traps in what is now India, is thought to have played a substantial role in environmental and climatic changes during this period. The Deccan Traps are one of the largest volcanic features on Earth, consisting of multiple layers of solidified basalt that were formed by successive volcanic eruptions near the end of the Cretaceous period. It is estimated that these eruptions covered an area of more than 500,000 square kilometers and released vast quantities of lava. Over the course of thousands of years, these eruptions spewed enormous amounts of volcanic gases, including sulfur dioxide and carbon dioxide, into the atmosphere. The release of sulfur dioxide from these volcanic events likely had immediate short-term effects on the global climate. When sulfur dioxide reaches the upper atmosphere, it can form sulfate aerosols that reflect sunlight back into space, leading to cooling, a phenomenon known as volcanic winter. This cooling effect could have drastically altered global temperatures and disrupted weather patterns, adversely affecting plant growth and the food chains that depended on these plants. In the longer term, the carbon dioxide released during these eruptions would have contributed to a greenhouse effect, potentially leading to global warming. This gradual increase in temperatures could have further destabilized the ecosystems already reeling from the cooling effects and other environmental stresses of the period. The timing of the Deccan Traps eruptions, with peak activity coinciding closely with the KPG boundary, suggests a significant overlap with the asteroid impact. This has led some scientists to propose that the combined effects of massive volcanic activity and the asteroid impact could have created a dual environmental crisis, making it exceedingly difficult for many species to adapt. The interplay between these two massive geological events likely resulted in a series of cascading ecological collapses, contributing to one of the most severe mass extinctions in Earth's history. Understanding the role of volcanic activity in the context of the mass extinction provides a more comprehensive view of the environmental challenges faced by late Cretaceous ecosystems. It underscores the complexity of factors that can influence extinction events and highlights the potential for multiple overlapping stresses to disrupt the biosphere significantly. Climate change and sea level fluctuations also played a significant role in shaping the conditions leading up to the mass extinction at the end of the Cretaceous period. These environmental factors, while perhaps less dramatic than an asteroid impact or massive volcanic eruptions, contributed to long-term shifts in the habitats and ecosystems that sustain diverse forms of life, including dinosaurs. During the late Cretaceous, the Earth experienced a gradual cooling trend that altered global climates and, in turn, affected sea levels. This cooling phase led to the regression of shallow seas that had once covered large portions of the continents. These shallow marine environments were crucial as they supported a rich diversity of marine life and provided foraging grounds for many marine and terrestrial species. As sea levels dropped, these habitats were lost, reducing the available niche spaces and leading to a decrease in marine biodiversity. The reduction in sea levels also had implications for terrestrial environments. The loss of shallow seas changed the climate further inland, often leading to increased aridity and the transformation of lush, wet environments into more arid, less hospitable ones. These changes would have placed stress on the plant species that thrived in more humid conditions, with cascading effects on the herbivores that depended on these plants and, subsequently, on the predators that fed on these herbivores. Additionally, The fluctuations in climate and sea levels likely disrupted weather patterns, potentially leading to more extreme seasonal variations that could have made survival more challenging for many species. Changes in precipitation patterns, for instance, would affect water availability not only for drinking but also for supporting vegetation. The gradual nature of climate change and sea level fluctuations meant that these stresses were exerted over extended periods, possibly weakening ecosystems and making them more vulnerable to sudden catastrophic events like asteroid impacts or volcanic eruptions. Thus, while these changes were slower and less visually dramatic than other extinction drivers, they were no less significant in shaping the conditions that led to the Cretaceous-Paleogene extinction event. This complex interplay of gradual environmental stressors with more immediate catastrophic events underscores the multifaceted nature of mass extinctions. It highlights the importance of considering a range of factors when studying past extinctions and predicting potential future ecological crises.